Okay, good afternoon. I apologize for the delay. Thank you for waiting. Let's get started. Is there any questions for me at this point? So I sent an email today rescheduling the simulation exam. It was scheduled for Monday, but there's two students that are going to be out on Monday, and I decided to postpone the exam until Wednesday. So Wednesday, same week. So Monday, we are not going to have a class, so you will have that time to work on your project. The project is due on May the 2nd. You're gonna have to do a presentation, basically expand on the presentation that you did for the proposal, which you're gonna show your model, your results, and you can also present the results that you got for the input analysis. So all that can be incorporated into the presentation. You will have from 10 to 12 minutes to present, and then the report is also due on that day. I posted a couple of examples online. So if you go to the assignment for the project, for the final report, you'll find two project reports that were submitted 3 years ago, and also a template for the presentation for the PowerPoint. So again, one more time, the simulation exam is rescheduled to Wednesday next week, so a week from today. Yes. Okay, so that's a good question. So if you face problems with the simulation, that is for the project itself, we can discuss on Monday, because that's a project day. So this Monday, or we will have to set up appointments during office hours or I cannot reschedule, because the university has some days in which we cannot assign anything between the end of the semester and the finals. So it's university policy. Yeah. So any other questions? Okay, so let's go to the lecture for today. In 7 part 1, we started discussing scheduling for production. Today we're going to continue that discussion in this lecture, and the agenda is here. We are discussing the goals of production scheduling, reviewing the scheduling research, linking planning and scheduling. We also discussing bottleneck scheduling, diagnostic scheduling, production scheduling, also in a pool environment. So in terms of linking, planning, and scheduling, so it's pretty obvious the connection between the two. You know, you have a plan in terms of what needs to be produced to meet the demand of your customers, right? So let's say you have a set of orders that are coming into your facility. So you have to make sure that you're producing to satisfy the requirement of the customers. In order for you to, there's no way for you to produce all the orders at the same time. So the idea is, how do you organize these orders so you can make the best use of your resources and deliver the products to your customers within the time that was promised. So typically you have a deadline, a due date, certain amount of days that you have to complete the order. So how do you manage to get the product completed for the order before that due date? So that's where scheduling is, why scheduling is important, because now you have a group of orders. Some of them are due on a specific day. So the days or the due dates will be different for all of them. The amounts are going to be different. So how do you sequence them in a way that you can make the best use of your resources and deliver the orders in time? So one of the strategies is called due date quoting. So you are taking into consideration the variability of your system, your capabilities, and the amount of orders that you already have in your facility. Taking into account all these variables, you promise a date to your customer. So okay, if you put this order today, this is how long is it going to take me to complete that order. So that's due date quote. So variability reduction, full production, and efficient batch sizing methods all make the production system easier to schedule. If you have a lot of variability, we saw in our previous lectures the impact of variability. Typically, it's going to take longer cycle times for you to complete a product or an order for your customer. So if you're able to reduce the variability of your process, you will have a better sense of how long is it going to take, and you have a way to produce to a certain deadline without having to account for all this variability that can impact your final cycle time. Another technique for simplifying scheduling is the due date quoting. So scheduling problems involving due dates are extremely hard. There are courses at the doctoral level that are just focusing on scheduling. So that's the level of difficulty and challenge that you have when solving these type of problems. There will be a class just for studying scheduling problems. So when we talk about due dates, these are problems that are extremely hard. So if they were easy to solve, it will be worthwhile to try to address these problems mathematically, but that's not the case. So we have to find other ways to deal with them. So this is what we refer to due date quoting. Here's an example. So you see here we have a line, a new job coming in. We have a line in front of the new job that's called the backlog. And then we have some units that are inside the facility. That's your working process. And then everything that's going out is what's completed. And that's what we call the rate out. So I have this equation here that looks at W, which is the WIP, plus B is the backlog, plus C, which is the new job, basically the time or the new job coming in. And then we put all that together. That gives us an understanding of how long is it going to take. Yeah, so I'm going to explain what that is right now. So typically, one way, so if you have this job, it's a priority type of job that you have to deliver quickly. One of the strategies that you can use to reserve some of your positions in the queue so you don't fully compromise your resources and you open these positions for jobs that have priority. So consider a CONWIP line that maintains, this is what we have here, a W, a WIP, standard units of WIP of whose output is in each period, or if or day, is steady with a mean, mu, and a variability sigma. So that's what we have here, CONWIP. So we are not gonna let anything go into the facility because we are going to keep a certain level of WIP inside the facility. So until we get a unit out, we don't let any other unit in. Suppose a customer places an order that represents C standard units of work. So that's what we are seeing there as a C, or that red dot is a new order that requires certain units of work, and we are free to specify a due date, right? So we get this order, and now the decision is for us when to specify the delivery for these units. To balance the responsiveness with dependability, we want to quote the earliest due date that ensures a service level of S, meaning that we want to meet certain level of service quality. S could be 90%, meaning that there's a 90% level of confidence that you are going to deliver these units on time. Of course, the due date that will achieve this depends on how much work is ahead of the new order. So here we have these many jobs. So anything that we promise, if this job has to wait for those to be processed, it's going to depend on how long it's going to take for you to complete the other orders. So this in turn depends on how customer orders are sequenced. So again, if you are going to put that order into the end of this line, you're gonna have to wait for all that. So that will be the sequence. First in, first out, right? So if you go in first, you should go first out. But there's other techniques or other sequencing strategies that you can use, like last in, first out. There are multiple or earliest due date. The ones that are due sooner are the ones that are gonna go first. So in manufacturing, you can adapt those sequencing for your orders based on what's going to work better for you at the end. So one possibility is that job are processed in first in, first come, or in which case we let B represent the current release list, which is going to be this backlog. So first in, first out, you have to wait for all that. And alternatively, if we can have those emergency positions that we just discussed that can help us mitigate the time that this new order has to wait. So this is for high priority jobs. So we can maintain them by quoting due dates by some lower priority jobs as if they were. So again, those strategies, you can, if you have first in, first out, you have to wait for all that to be completed. But if you have a high priority job and you have some emergency positions, you can adapt your sequencing to jobs that have higher priority and place them on those positions. So you can see all the variables, you can see all the things that can impact your quoting for due date. So there's an analytic approach, which is listed here. We have some notation. XT is the work completed during period T. Mu is the mean work rate, is standard units per period. Sigma is the standard deviation of the work rate. M is the work ahead of and including current job. So these are the number of jobs that are waiting before you arrive. S is the desired service level. This is a probability, right? So, and then L is the minimum due date to attain service for current job. So this is the minimum due date that you are going to be allowed to have if you want to achieve that service level. So we have a probability here, the probability that this summation from T equals 1 until L, which is the minimum due date to attain service for current job, of the work completed during period time T has to be less than or equal to M, which is the work ahead of and including the current job. This probability has to be greater, or I mean, it has to be equal to this service level. So this is the probability of not completing M units of work within the lead time associated with this production schedule. So this is the required condition, and then to quote the due date, we have this equation. So knowing that we have a specific service level that we want to achieve, that service level is S, we have this equation that can help us establish the due date to quote our customer. So you see, this is a very, there's a probability associated here with the Z values. Z is coming from the standard normal distribution. So depending on that level, as we are going to compute, the service level is going to allow us to compute these Z value from the normal distribution. So S is this little s next to the Z value. So the probability is associated with this desired level. And then once we get the probability and we have the information about the mean work rate and the standard deviation in terms of variability, we can solve this equation for the minimum date to attain service for that job. So L is going to tell us, okay, if you take into account the variability of your system, the production rate, and the desired level that you want to provide to your customers, the service level, this is the amount of dates that you have to wait to be able to, or this is the minimum number of dates or the due date that you might quote your customer for. So M, again, is the work ahead of and including current job. Mu is the mean work rate. So in an ideal world where there's no variability, this area that is circled here, we don't have to worry about that. Right? The lead time is going to be just N, which is the number of jobs divided by the production rate. But we know there's variability, right? So we have to account for the variability in the system in order to establish that lead time. So some additional observations here. I think I already discussed this. So if variability equals 0, then L equals M over U, regardless of the service level that you're trying to address, because there's no variability, so you'll be able to satisfy the customer with this specific lead time. So quoting N over mu days will achieve 100% service in any system, in a system with no variability. The due date is increasing in sigma. So the more variability will require the more safety lead time. So the more variable your process, the more time you are going to spend producing these products, and more time you will have to, customer will have to wait to get the products. So in order to achieve service level of at least S, we must round up to the days or to the next integer to arrive at the due date to quote in units of full days. So let's look at one example. Here we have the probability service level 0.990%. We can compute the standard normal table for 0.9, it's 1.28. M is, mu is 100 pieces per day. Sigma is 30 pieces per day. The WIP, 500. V is the number of pieces in backlog, so 900, and C are the 100 pieces in current job. So if we put together, or if we add up W or WIP plus the backlog plus the current job, number of pieces in the current job, we have 1,500 pieces that have to be completed so we can deliver these orders. So going back, basically taking into consideration all the variables in this system, we can compute that lead time using, or that minimum due date to attain the service for that current job using this due date quote equation. So in this case, after adding these two pieces into the equation, you see that 1,500 divided by 100 is 15 days, right? So without variability, it's going to take about 15 days. But this variability associated with the process is adding 1.56. So you have to go to the next day, 2 days of additional time in order to complete this order. Yes. The 1.28? Yes, so that's coming from the standard normal distribution. Oh, so that C is for 0.9. Okay, so that's the service level. That I understood the question now. So that's the question. So how do you know which C value? Yeah. So Z is for S. S is 0.9. That's the service level 0.9, 90%. So you're going to find the Z value for 0.9. Yes. Yes, 1.28, correct. Any other question? Okay. So as I mentioned, know that this M divided by M equals 15 days. So to accommodate the variability, we're building in 2 days of safety lead time into our code, because we have this variability in our process. So that's increasing this lead time for promising a due date for this order. Okay, so again, we have to take into account the web, the backlog, and then these orders coming in. So we have to quote the date, all the web, all the backlog, and now this new order. How long is it going to take me to get you that order? 17 days. Another example, this is scheduling via lot sizing. This is TJ International Paralam product. We have 3 processes for this product, which is wood, leg clip, press, and saw. And the issues are the press is the bottleneck. There's 12-hour changeover time to switch width. So we have 4 different widths for our product, 12, 14, 16, and 19. And many products made from each width, but less for the 14, 16 than the 16, 19. Currently try to run at least a week between changeovers, seasonal demand, inventory buildup in off season. So these are some of the issues, right? So we currently try to run at least a week between changeovers, because there's a 12-hour changeover. So every time you switch from one product to the other, you have to spend 12 hours. So obviously you want to avoid changing this between products until it's really necessary, because you're going to basically lose 12 hours of labor. So the problem is to determine run sequence each month. So here's the notation. We have H is the hours available in terms of days per month and hours times hours per day. U is the desired utilization. Capital DI is the monthly demand for product I. DI is the hourly demand for product I. So we can use the monthly demand to get the DI, or the little DI. PI is the production rate, parts an hour. SI is the setup time in hours for product I. Next I is the lot size, parts per product I, which is our decision variable. So essentially what we want to do here is, okay, I know I have a changeover that is going to last this many hours. So I want to know how many parts per lot I should produce before I move from one product to the other. So my decision variable is Xi. This is what I'm interested in finding. Lot size for product I, that's my decision variable. So the problem, choose lot sizes for the month to meet demand as efficiently as possible. So what is the approach? We fix the lot sizes for all products and compute number of cycles that can be run in the next month as follows. So we have capital N. U is, again, the desired utilization. H is the hours available. DI is the demand. PI is the production rate. All of that divided by SI. SI in this case is setup time. So I don't want you to get confused. So what we just did here, we defined this notation, and it looks like, well, it's not look like, but now we're going to use some of these notation, and it's going to have a different meaning. So S in this case was the desired service level. For this scheduling via lot sizing, S will have a different meaning, which is the setup time. Okay, so there's 2 separate. We are looking at 2 different animals. Okay, one is for quoting the due date. This is looking at the lot size for scheduling. Okay, so if the horizon is short, n should be rounded down to the nearest integer. Otherwise, a non-integer n is okay, since you will be rescheduling anyway. So the lot size will be equal to xi, which is our decision variable, and is going to depend on this demand for I, right? DI is the monthly demand for product I. I is the product, and n is the value that we computed using the equation at the top. This, of course, needs to be rounded or ceiling. Problem is, you don't necessarily want to make the same number of runs of a low demand product as of a high demand product. Right? So if you have a low demand product, you don't want to do 4 cycles of production for that product because you're producing too much. Right? You don't want to produce too much of a product that is not selling. So if you follow this process, you might end up doing that. So you don't necessarily want to make the same number of runs of a low demand product as a high demand product. So as a fundamental issue for non-cyclic schedule, what is the objective? Okay, so in our case, are we trying to minimize the sum of the run lengths? If we write out the Lagrangian for the nonlinear optimization problem and optimize some continuous lot sizes, we get that x, which is our decision variable, is going to be equal to the square root of these mu times di, si, and pi. So going back to the notation, di is the hourly demand, pi is the production rate, and si is the setup time. All of that in hours. So the lot size is going to be the square root of these parameters, multiplication of these parameters. Where mu is not given, is also find out using this summation of the square root of di times si divided by the production of that product divided by u, which is the utilization minus the summation of this ratio di times pi. All that squared. So we need to find mu in order to find the decision variable. The problems are, since we solve for lot sizes, we wind up with a non-integer number of setups for the month. How do we allocate the setup time? And what order do we run the product in the non-cyclic schedule? So these are two problems. So we should solve for the number of run cycles for each product. But the question is, what objective should we use? So that's where we define this minimax schedule, in which we minimize the maximum run length. So now we want to say, okay, I know I have to decide how long I'm going to run these products, how long before I switch to the next one. But I don't want to extend that too much, right? So what I'm trying to do is let's find out that length that is the minimum for all products. So for what is the maximum run length that minimizes the summation for each product? So we are never too far away from changing over to another product, perhaps a good surrogate for maximizing flexibility. So how do we do that? Let's look at this notation. Ni is the number of times product I is run in H. Okay, so H is again the time in hours. These are now our decision variables. So we want to find the number of times product I is going to be run in this time period. And we know every time we switch, we are going to do some changeover. And Si plus Di, which is the demand divided by Ni times Pi, is equal to the run length each time product is produced. So using all this information, we can formulate the problem. This is the integer programming formulation, in which we are trying to minimize the maximum run length, T, subject to these equations. NS, or the summation for all products, NI times SI, has to be less than equal to the utilization times H minus the summation for all products of the demand divided by the production. This is the capacity constraint. And then we have the minimax constraint. As you can see here, this is what's defining the minimax. This is trying to minimize the maximum run length. And we want to make that less than or equal to T. We want to make that amount as small as possible, because if you look at the objective function, you have that T value right there. So as you minimize T, you are making that constraint smaller. And that is also constraining the maximum run length for each product. And that's how this formulation works. You're forcing T to be as small as possible. As you force T to be as small as possible, you're also minimizing the maximum run length. So, for example, here we have H equals 396 hours. We have a utilization of 0.9, and we have 4 products. We have the demand for each product. We have the production rate for each product. We have the SI. What was the SI? Do you remember? The setup time, right, in hours. And then we have the ratio for the demand and the production rate. So for example, that ratio, 150 for product 1, 120, 6.7, and 5. So you can produce more parts of 1 than for 4 in an hour, right? That's you can see that from the numbers. Setup time is smaller for product 4, and the ratio in terms of product and demand and production is given as well. So the total production time required will be 281.67 hours. How do you get that number? You add up these amounts. The 289.7, 81.7. So the minimum run time or run schedule, suppose that the plant has a policy of never making less than 1,500. So the current lot sizes are 1,500, 1,200, I'm sorry, 15,000, 12,000, 1,500, and 1,500. So if the plant has a policy, so for example, here you only need 500, that's your demand. Here you only need 250, but the plant has a policy that you never make that less than this, 1,500. So your lot sizes will not be smaller than 1,500. So the current lot sizes are the amount that you need for product 1, product 2. And then for those that are less than 1,500, you're going to produce at least 1,500. So if that's the case, this takes 19.2 days, close to the 22 days available. But it means that some product won't be produced until pretty late in the month. Okay, so the number of cycles per month, going back to this equation right here, N will be equal to 2.87, which will lead yield lot sizes of, so if we divide these amounts, 1,500 by the number of cycles, you'll get 5,219, 4,175, 174, and 87. But N equals 2.87 means that the first 2 cycles in the month use the above lot sizes, while the last one uses reduced lot sizes, right? So we are not, they say that you cannot produce if it is smaller than 1,500. So we can implement the formulation as follows. So going back into this, so how do we fix this problem? We can implement the follow formulation. We start with n equals and I equals 1 for all i's. Note that the product with the maximum run length is product 1 with a run of 158 hours. Then we add the setup for product 1, so n1 equals 2, and its max run length becomes 83. And now product 2 has the longest run length at 128 hours. We add the setup for product 2 at n equals 2, and its max run length becomes 68, right? And now product 2 has longest run length of 83 hours. We continue adding the setups to product with the longest run until we run out of capacity, and the optimal solution will be this one right here. So we end up with 4 cycles for the product 1, 4 cycles for product 2, 1 cycle for product 3, and 1 cycle for product 4, with xi equals 3,750, 3,500, and 250. So the schedule goes as follows. So that's based on the information. So for example, here, we know we only need 1 cycle for these 2 products. So we can get those out of the way as soon as possible and then focus on the other 2 products. If you start with product 1 and product 2, you have to run 4 cycles of those. It will be until the end of the process. It's going to take too long for you to get these 2 products out. So it's better to start with these 2 and then continue, get them out of the way, and then continue with the other ones. So we will set up for the 4th product and get it out of the way. Likewise for the 3rd one. Now we run 3,750 of product 1, 3,000 of product 2 in succession for 4 times. The longest anyone will ever have to wait to be will be for product 2 at the beginning of the month at 3.73 days. After that, the longest wait will be 2.53 days. So in conclusions, the Minimax schedule results in shorter wait for product than either minimum run schedule or cyclic schedule. And it's simple to compute, which is the last thing with it. So we take the amount, we add the setup, and then we continue searching for the one that's taking the longer, split it, we add the setup, and we continue in that fashion. Okay. So let's talk about bottleneck scheduling. Now, we remember scheduling in the pool environments, we have simple conweb lines. So these are lines that are maintaining a constant web. Simple sequence sufficient and with no setup. Again, conweb lines with share resources, no setups need to augment sequence at share lines, and they have a first in, first out at the share resources. So this is an illustration of what's going on. We have routing A, routing B for these products, but as you can see, as soon as you get the one out, you continue the process, keeping going in and out based on the units that are leaving the system. So when you have conweb lines with setup, sequence still reasonable. You must balance capacity loss with due date requirements. Finding an exact solution is impossible. So a heuristic starting with the earliest due date and rearranging the sequence can work well. You can just list all the works, all the jobs in terms of the earliest due date, and then start picking from the top of the list. For general environments, many routing makes simple sequence insufficient. So backward scheduling based on due dates may be infeasible. Forward scheduling may be suboptimal. So again, what we're trying to explain here, as I mentioned at the beginning, scheduling is very challenging. There's a course only for scheduling. So what we are trying to give you here in this discussion is more in terms of, I mean, if you're faced with these environments, what are the type of things that will work better? So sequencing example, we have 16 jobs. Each jobs take 1 hour of single machine. This is our bottleneck resource. We have 4 hours set up to change families. We have fixed due dates. So the question is, can we find a feasible solution if possible? So here are the 16 jobs. We have the different product families. We have the due date for each product. We have the completion time. So in this example, jobs are sequenced in terms of the due date. You see here, column 3, the jobs are sequenced according to their due date. So when you look at and this is a heuristic, okay? There's no formal mathematical procedure here. We're just taking the jobs, we sequence them or order them in non-increasing way based on the due date. And then we have information about the completion time based on the data that we have. And then based on the completion time, we can compute the late, right? So a negative number means that you are producing before time, right? So it's early. Positive number is late. So if you sequence these jobs in this way, you get an average tardiness of 10.375. So that's by looking at the average of this column. So that's based on EDD. But we can improve on this approach. We can get started with that approach, but then we can improve by considering all pairwise interchange. And now we can start making changes in the sequence and see if we can get some improvement. Choose one that reduces average tardiness by a maximum amount and continue until no further improvement is possible. So, for example, in this slide, I'm showing an exchange between job 4 and 6, 4 and 5, sorry. So 4 and 5 are switched. Now, based on that, we get an improvement in terms of the average tardiness of 5, reduction of 5.375, just by swapping one job. So it looks like that job was creating most of the problem or very high, let's see, 4 and 5. So by swapping that, we'll get a reduction on the average tardiness. And if we continue that process of changing, like for example, 8 and 7, this job 10 was swapped up till this point, making that continuous swapping and looking for the average tardiness every time we do a swap, we can reduce that average tardiness to less than 1, which is 9.8075 lower than the EDD or earliest due date. And if we continue the search, again, these are greedy approach, as we stated in one of the slides. We continue that search. Obviously, this is you can program this. You continue doing this swap until you find the best improvement. You can obtain a sequence that will give you 0 tardiness. Diagnostic scheduling. We're getting towards the end of the lecture. So the goals are to schedule at the appropriate level of detail for environment, make use of realistic, obtainable data, and accommodate intangibles in decision support mode. So what is the approach? deterministic model based on conveyor models released as late as possible, subject to due dates, and provide diagnostics on infeasibility. So what are the types of infeasibilities that we are looking for? Working process and capacity. Can we move due dates or increase capacity? So we want to achieve this appropriate level of detail for the environment that we are working on. We can start with a deterministic model, basically saying that there's no variability in our system, and then we start looking at what will be the release as late as possible, subject to the due dates, and then look at what are the infeasibilities that are given based on that model. Type of infeasibilities that we will search for is what will be the WIP, how big is the WIP, and how well used is our capacity in terms of utilization. So in scheduling feasibilities examples. So for example, we have a capacity of 100 per day. The minimum practical lead time is 3 days, and the working process in the system with 1, 2, 3 days to go is 95, 90, and 115. So by looking at this feasibility deterministic model, days from the start, by looking at the day from the start, like 1 day after the start, 2 days, 3 days, 15 days after the start, the amount due is listed in the second column, and the cumulative amount due is on the third column. So you see that number is going to start increasing according to the amount due per day. The cumulative capacity, 95, 185, 285, 385. So it's increasing by 100 every day. And you will see that for the second day, right there, we don't have enough, right, to cover that cumulative amount due. And then that happens in terms of WIP, and then in terms of capacity, that happens in period number 8, which we have 785, and then the amount due is 790. So these are the type of infeasibilities that we will be searching for using these deterministic models. We have the starts from the day, we have the amount due every day, we can compute the cumulative amounts, and then based on the amount due and the capacity that we have available, we can specify if there's any feasibility in the system. And there's a plot here. You can see when the cumulative capacity in red is above the due, which is in blue, we are okay. But if the blue is on top of the red, it will be that we are not capable of meeting the demand. So here we have the difference. So it's plotting the amount that we have in terms of surplus, in terms of units, so per day. So there's one item here, second day, in which we go below and then we go up again. But then after period 7, you see that we are not meeting, we don't have any surplus. So there's a capacity infeasibility happening at that point. So what are the scheduling takeaways? As I mentioned already, scheduling is hard. Even simple toy problems generate complicated mathematics. Scheduling can be simplified through the environment by due date quoting, flow simplification, sequencing in place of scheduling. Finite capacity scheduling is coming, but in what form is unclear. shifting bottleneck, genetic algorithms, rule-based systems. So these are all areas of research. And diagnostic are important in scheduling. Pure optimization generally is impossible, and there's a need good interface to allow human intervention. So that's the last slide. Any questions? Yes. Question was if for the final exam there will be true or false questions. The answer is yes. Yes, I said I was going to post it by the end of the week. But remember, that's not going to be included in the exam. So, I mean, I'll post the solution, but since I'm posting the solution, all of you will get a full score for the last lab. Okay. That's a good question. So yeah, I can make it due on Monday if you want. No. I mean, I can work with you. If you think it's too much, I can extend it. I'm not. Yeah. So remember, the best way to prepare for the exam, simulation exam, is to go practice lab 6, 7, 8, and 9. If you know how to build those labs by yourself, you should be well prepared for the exam. The other thing is that you can bring a paper with, for example, if you need to write down, this is how you compute the cycle time, you can put it in a piece of paper and you can use that as part of the exam. No, I mean, what I'm saying is right now is due on Wednesday, right? If you feel that you cannot submit by Wednesday, send me an email and we'll extend it. Okay. Yeah. I mean, but if you want to make it due this Monday, you can submit by Monday. It will not make a difference. Oh, okay. By the day of the presentation of the project. Okay. Yeah, I can extend it to Monday. It's not the issue. Good. I was talking about Monday next week. That's yeah. Yeah. But yeah, that's fine. Again, I'm not here to punish you, but if you need more time, just let me know. I will extend the deadline. Anything else? I know it's getting difficult, challenging. It's getting towards the end of the semester, so a lot of things happening. So I try to be more flexible at this point of the semester. In that case, if you need more time to submit the homework, just let me know. Any other question? Good. So I'll talk to you again next week.